All right. I handwrite most of our notes from chapter 12 just because I like to do the examples as we go along. Chapter 12 is stoichiometry. And you do have to have a thorough understanding of mole conversions to find success. So hopefully we get where we need to be here. Stoichiometry. And I loosely follow chapter 12 in the textbook if you're ever looking for a reference point. Stoichiometry describes the process of calculating the amount of one substance let's say from a provided amount of another. So stoichiometry, this is our process of calculating the amount of one substance from the provided amount of a different substance. Hang on, let me pause. All right, for every single stoichiometric calculation that you're going to do, you're going to have something called a mole ratio. A mole ratio is found from a balanced chemical equation. Most of the time, you're provided with the balanced equation. Sometimes you have to balance it first. For example, let's use this balanced equation. I always like this one because it gives us lots of coefficients. All right, so if this is our balanced chemical equation, we are going to be looking at the coefficients of each of the compounds in order to create our mole ratio, okay? So for instance, if I wanted to know the ratio of aluminum to oxygen, it is 4 to 3, right? So in this balanced equation, for every 3 oxygen molecules, there are 4 aluminum molecules. Same thing, I could look at the oxygens. If I have 3 oxygen molecules, I should be able to complete or to create 2 formula units of aluminum oxide. That's what these coefficients mean. We need to write these, though, in a meaningful format. So instead of writing it just like the 4 to 3, like a ratio, we want to put it in a way that we can use dimensional analysis. So I would write this as 4 and then moles of aluminum, because that's what that means. There are 4 moles of aluminum for every 3 moles of oxygen. And of course, the reciprocal is also true. You could have this as 3 moles of oxygen for every 4 moles of aluminum. You can see that this If we have this right here, we are going to have the ability to convert. If I have moles of oxygen on the bottom and I have moles of aluminum on the top, that means I'm probably going to cancel out oxygen and I'm going to get aluminum, or vice versa on the other side. So mole ratios. Does anybody have any questions about where I got this from? Because if you can't build a mole ratio, you can't solve a single stoichiometric problem. Not one. Do what? Right here. Yep. Coefficients. Okay. Let's use the same balanced equation then, and let's do a mole to mole problem. And these are by far the most simple, and they're going to be included in every type of stoichiometry problem. This is a one step, which is the only one that's one step. The rest of them are 2, 3, and 4 steps. So we have our mole to mole here. So let's say we're using the same balanced equation from here. And in this case, I have been given 16.5 moles of aluminum oxide. And you're asked to determine how many moles of aluminum were used to create that. All right, so in this case, I have a given, I have an amount that I know, and then I have an amount that I'm needing to find. You can tell that this is different than just the mole conversions that we've been doing, because I have one substance here and a different substance in my unknown. So we know we're doing stoichiometry. That's the first thing I want you to start really ingesting. This is different than our chapter 10 material. I have one substance and I'm going to a newer, different one. So that should automatically trigger the fact that you're going to have to use a mole ratio in order to solve for this. So we have 16.5 moles of aluminum oxide. We are not going to change a thing about dimensional analysis. We're still going to draw a fence. That has not changed. 16.5 moles of Al2O3. I am going to strongly recommend that you write your compound when we write our problems out. All right, so here's step one, the given. I'm writing both the unit and the compound. This is the same process. We're just kind of tweaking it a smidge. Whatever I have here, I have to have down here. So I don't just have to worry about the moles part. I do have to have moles, but I also have to have moles of aluminum oxide. My unknown is right here, and it's not just moles, it's moles of aluminum. Because I have two different substances, this is going to be the mole ratio. The mole ratio is found looking at the coefficients of these in our balanced equation. So I locate aluminum oxide, the coefficient is 2. So there are 2 moles of aluminum oxide. And then here I have aluminum, the coefficient is 4. Moles of aluminum oxide will cancel out, and now I will have moles of aluminum, which is what I'm trying to get. Some questions I usually get are, do I have to simplify this? So 4/2. You can if you want to. I don't care. If the math is going to work the same way, if you want to simplify and then do the math, that's fine. Generally, I don't, just because most of these are multi-step, and I'm going to end up, just multiplying and dividing anyway. As with all dimensional analysis, you're going to multiply across the top, and you are going to divide by the bottom. So I have 16.5 times 4 equals divided by 2, and my answer is 33 moles of aluminum. And actually, that should be 33.0, but I won't freak out on that right now. That's it. Yes, ma'am. The balanced equation, the coefficients of the balanced equation. Sometimes you have to balance it yourself. So there's your very first stoichiometric problem. Ta-da! All right, let's do a couple more. And then we'll move on to, all right, let's do, again, I'll just keep the equation simple. Let's decompose water. If we decompose water, hold on, nope. I need my, where's my white hat pen? I did not need to write a 2 there. Sorry, my bad. All right, so here's our balanced chemical equation. I have 4 hydrogens, 2 oxygens, 2 oxygens. I'm good to go. Remember, our mole ratio is going to come from the coefficients. If there is no coefficient there, it's understood to be a 1. It's not a 0. It does exist. There's one of them. We just don't write ones. All right. So in this example, let's say we've been given 25 moles of water, and we need to determine how many moles of oxygen this will create. Again, I'm automatically going to check, am I doing just regular mole conversions or stoichiometry? I can tell I'm doing stoichiometry because I have 2 different substances. Anytime you have 2 different substances, you're going to have to use a mole ratio. So I'm going to go ahead and I'm going to set this up. And I'm going to put my given just like I have been a million times before. If I have moles of water, I need to have moles of water down here. And then I'm going to have moles of oxygen, which is what I'm trying to get to right here. So this is, again, my mole ratio. Mole ratios are found using the coefficients in the balanced chemical equation. So I'm going to locate water. Here's water. The coefficient is 2. Then I'm going to locate oxygen. And since no coefficient is listed, it's understood to be a 1. Moles of water now cancel out. I will have moles of oxygen. 25 times 1 is 25 divided by 2 is 12.5. Questions? Like I said, this is like the base. You're going to do a mole ratio in every type of stoichiometric problem. So it is it's absolutely mandatory that you understand how to use the mole ratio and how to convert when just this simple mole to mole conversion. Yes, ma'am.
So it will always be like
For our practices, yes, I will, but no, for our tests and stuff, I'll probably throw some in that you have to balance. All right, let's try one. You try this one on your own. We're going to use the same balanced equation. Let's just make sure before we move on to anything else that you can find the correct answer. Let's say in this case, you've been given 7.5 moles of hydrogen. And I want to know how many moles of, I don't know, water. So same balanced equation. If you didn't write that down, I'll have to scroll down for it.